Hello everybody, my name is Chris Brady, author of the Boeing 737 Tech Guide and the Boeing 737 Tech Site. And this presentation is about the 737NG Performance Improvement Package. So I'll be giving you an overview of the Performance Improvement Package and then looking at the individual changes. So they include the anti-coals, a environmental control system in inlet and exhaust, wheel well fairings, slats and spoilers, and the CFM56-7BE Evolution engine. As always, please treat your company training and their manuals as the authoritative source of information. Okay, so for the overview, how this came about was that in an attempt to keep the 737 as competitive as possible against its competitors, i.e. of course the A320 family, Boeing's always been continually looking at ways to either save weight, reduce drag, reduce fuel consumption or increase performance. And to be honest, this goes right back to the very first 737s, the 100, and you'll have seen in the flaps and slats presentation I showed you the difference between the leading edge flap design and in fact the slat sequencing. Now that was done at, I recall, about line number 100, 150. So it goes back that far. Now these changes are often added in isolation, and are usually made as incremental changes over the lifetime of the generation. And where possible, Boeing always try and offer them as a retrofit onto earlier aircraft, just so they don't, sort of offside those who've bought aircraft already and, want to take advantage of the upgrade. Sometimes these carry a name if there are big enough improvements, like going back the 737-200 Advanced, and sometimes they don't if they're individual. It's kind of Boeing's shout on that. But this one was called initially it was called Fuel Burn Improvements. That was the working title, but it became known as the Performance Improvement Package, or the PIP. And as I've said there, this one was announced in Feb 2010. Boeing didn't go as far as calling the aircraft 737NG PIPs, but it was kind of understood. So an overview of the improvements. So the PIP, it was a series of aerodynamic and engine improvements, and these included refining the wing control surfaces, a redesigned wheel well fairing, streamlined anti-collision lights, the environmental control system, inlet and exhaust modulation, and the new Evolution engine. The total fuel saving with PIP was around about 2%, so really quite impressive. It was introduced as standard, and by that I mean it wasn't an optional, and there was no cost implications, so it was free of charge. And it was something you couldn't opt out of. And this was introduced into production NGs in stages between March 2011, which was about line number 3570, and December 2012, which was line number 4302. So it was introduced over this sort of 18-month period. Now some of the improvements are available for retrofit to earlier NGs, but not all of them, and I will come on to those throughout the presentation. The graphic on the right there, that's a little summary of the before and after, if you like. Most of the changes are visible on the underside, which is why I've got these two photos to compare. The one at the top's pre-PIP, your basic NG, and the bottom one's got the PIP. And you can see the basic changes on there to the engine, but the visible part being the engine exhaust. The ram air exhaust is quite visible. The wheel well fairings you'll be able to see on a walk around, The spoilers and slats, that's quite subtle. You possibly could see the difference, but you'd really have to have two aircraft sat next to each other to be able to pick up on those. Anyway, on with the presentation. So first point is the anti-colds. This is very obvious, as you can see in these photos. This was introduced in March 2011. Both the upper and the lower anti-collision lights were changed from this old cylindrical shape that you see in the upper photo to a much more streamlined oval shape with fairings around it, all in the name of drag reduction. The upper anti-collision light only, the upper skin had to be revised to reduce the risk of cracks. That skin revision eliminated the weight reduction milling of the skin doubler in that area under the light. Because of that structural change, no retrofit was possible. So this is actually quite an easy way to identify whether your aircraft's a PIP aircraft or not, and therefore you can age it to, if you've got the old shaped anti-collision light, you know the aircraft was built before 2010, or in 2010 or before. If it's got the new shape light, then you've got a 2011 model or newer. The ECS environmental control system, inlet and exhaust. So what, again, PIP is trying to do here, that the whole thrust of it is drag reduction. Now, it reduces drag here by modifying the old ram air inlet systems, well, inlet and exhaust. So what it's doing is it's adding a new modulated ram air exhaust system for the air conditioning packs. The inlet and the exit, they're tuned now on PIP aircraft. They're tuned to open and close together. The inlet doors and the exhaust louvers will now open and close together in harmony at a very specific sort of relationship to optimize thrust recovery of that air exiting the exhaust louvers, and that reduces fuel burn. These changes were brought in from line number 4302, so December 2012. So it's the latest of the changes, and this is another one where retrofit isn't available due to the structural changes. So if we have a closer look at those two parts there. So taking the inlet first, the previous ram air inlet actuators, they've been replaced by these new smart actuators, and they give position feedback and communicate with the new added ram air exit actuators, which are attached to the louvers that you'll see on the walk around. You won't be able to see any difference to this to the inlet actuators on the walk around. There is a difference. They're actually mounted at a slightly different orientation than the previous ones, and they require structural changes, quite subtle structural changes to the aircraft, which is why a retrofit isn't available. But I've stared long and hard at both, and I personally can't see the difference. That's not to say you won't, just that I couldn't. These inlet actuators are not only the one obviously visible in this photo that I'm showing you here, because that's just the deflector door. It's actually hinged further back as well, and the whole thing moves to vary the air intake. On the exhaust side of it, it's much more easy and obvious to see. Upper photo is pre-PIP and lower photo is with the PIP. So the upper photo shows the old plain oval shaped duct opening, and the lower one you've now got this rectangular shaped duct with three exit louvers. I mean, they could have kept it oval and still had louvers, but I think the louvers were just easier to build to fit a rectangular aperture. Hence, they went in that direction. So these louvers are actuated by a combination of shafts and linkages, or as we used to say, a suitable system of levers and pulleys that are driven by these added exit actuators. Again, for installation, structural changes have had to be made for the wheel wells on both sides of the aircraft. Obviously, because there are two of these ducts on the left and right side of the aircraft, and that means that retrofit isn't possible. So this again remains a way to tell if your aircraft is older than December 2012, whether you've got the old oval exits or the louvered ones. Now, why am I showing you a photo of a classic? And yes, this is a classic, is because I just found this cute to know that, you know, that not only is there nothing new in aviation, that there's nothing new in the 737 really. A lot of classics had louvered ram air exits, like the one in this photo. The only difference really is the an obvious difference is the shape. These are kind of squarish, whereas on the NG PIP they're a sort of longer rectangle. But Boeing actually started off with these louvered ram air exits on the classics, and then binned the louvers and just left plain rectangular exits without the louvers. They took them off. I don't know why. I would imagine they didn't think that performance benefits were strong enough to keep the weight and the mechanics of the system. If anybody does know, I'd be fascinated to know the background to why they took them off. I believe the difference on the classic louvered system and the PIP louvered system is that the classics were mechanically controlled, whereas the PIPs are digitally controlled. But I'm not too sure on that. That's a little bit beyond my knowledge. Again, I just had to show you this to show you that, you know, anybody still flying the classic might say, well, you know, this is not new, and you're absolutely right. And I find it surprising that Boeing went away from the louvers on the classic and introduced non-louvered NGs and then brought them back in again. But there we go. Alright, onto the wheel well fairings. This one's a little bit more straightforward and cut and dried. You can spot the difference in the wheel well, and again, I know a lot of you guys like to go away after having seen the video and, you know, see these things on the real aircraft. So what Boeing did here was on the aft half. So that's the half that faces forward into the airflow of the wheel well fairings. These areas known as the ski jumps. They've been redesigned from the old rectangular shape which you see on the upper picture, where it's just a simple 90-degree lip, to a curved form. Again, in the name of drag reduction. You get rid of corners, you replace them by curves, you reduce drag. They obviously didn't think it was worth doing on the forward half, because that kind of trails into the airflow. I guess there would have been some benefit, but obviously not enough to justify this. But the aft half's the one where the step really impinges on the, you know, in the direction of the airflow. So that's the ones they changed. This is a slightly, well, it's a different photo, better or worse. It kind of shows you the difference here between the old and the new, and what's been done. But you know, if you just run your finger across it, where next time you're in the wheel well, you can feel the difference. You can feel the sharp edge on the old system. So anyway, these new ones were standard from March 2011, so they were an early adoption of the PIP program. Again, line number 3570. They are available as a retrofit. I don't know if anybody's bothered doing it, but it's there if your airline's particularly green and eco-friendly, then they may have done it. But it's just a customer option. So I guess it's one of those things. If you look and you've got the new ones, you don't necessarily know that your aircraft was post March 2011 because it could have been a retrofit. All right, onto the slats and spoilers. These changes are really quite subtle. Very, very, very hard to spot if you can spot them at all. But I'll cover them because they are, you know, quite an important part of the whole package. So the trailing edges of the slats were reduced in thickness. They were basically made thinner by replacing the old fiberglass filler that was in there with an aluminium machine tapered arrowhead. So they got the thickness in the trailing edge wedge down from 0.06 of an inch to 0.02 of an inch, which, you know, we would probably think, why bother? But the aerodynamicists did the work on this, and that trailing edge step, you know, be it only 0.06 of an inch, was enough to create a stagnation point, you know, behind it, and hence a vortex as the air flowed over it. Which, and you know, vortices, you know, whilst they can be useful in, you know, localized places for lift, what you can't escape is the fact that they give drag. So again, in the name of drag reduction, these trailing edges were machined down in thickness down to this new fine level. The spoilers got the same treatment. So all of the flight and ground spoiler trailing edges, except 2 and 11, for some reason, and I'm not quite sure what that is. They're the outboard flight spoilers. They were reduced in thickness by 60%. Again, to reduce drag by reducing that aft-facing step. The method was slightly different, so there was no honeycomb on this part, but they had been extruded aluminium fillers, and they were replaced with machine tapered ones. And again, machine tapering you can make far more fine and thinner. So the step, as you see there, is reduced from 0.14 of an inch to 0.057. So you know, well, that's half as thick. The other thing they did was reduce the thickness of the rub strip as well, and that's pretty much halved in thickness. The last thing they did on here was to reduce the spoiler gap, and again, it's difficult to spot, but this is probably the one of all of these that you might be able to spot. So this photo I just managed to take at the right angle, looking over the wing. What I was actually taking a photo, or trying to get a photo of, was the 737 with the Concorde in the background. This I took just before an air test from Filton on the 737, which was going off to, I think it was going to some country airlines in the States. Anyway, that's Concorde, that's Filton. But let's get back to the spoiler gap. So it's the gap between the spoilers and their respective flaps. That's the gap they were going for. Now these were actually historically set to a higher than nominal position. So the gap was built in to improve the lateral control handling qualities on, in particular, the 737-700. So it wasn't actually necessary on the 8 or 900, but for commonality in the manufacturing process, the gaps were left there. Anyway, when the aerodynamicists were looking at ways of reducing drag, and you know, this spoiler gap was questioned. The Boeing got on the case and made, now I haven't managed to get any concrete definitions, if you like, any concrete examples of what they did, other than one statement where they said that they made various lateral control system changes. So whatever they were, these various lateral control system changes were made. They then did the analysis and the flight tests on these, and they found that the revisions met all the stability and control requirements, so the gaps could be reduced, which they subsequently did. These changes were made standard again from line number 3570, so March 2011 onwards, and all of the new spoilers and slats are fully interchangeable and intermixable with previous spoilers and slats. So it's all the bits marked in red on the graphic there, and this is important because if a part gets damaged or needs changing for whatever reason, Boeing or wherever they come from don't want to be holding a stock of old parts, or an aircraft not to be able to fly because it can't get an old style part. So the new parts, which are the ones which are in production, which will you be able to get hold of more easily and probably cheaply, they can be switched out on an existing aircraft. Alright, this is the big change. This was really kind of what the game changer was. The 7B Evolution engine. This was announced back in April 2009. CFM redesigned several components of the 7B engine and named the new one the 7BE, where the E stood for Evolution. They used, as they say in their literature, 3D design techniques to improve airfoils in the high and low pressure turbines to improve engine performance. In addition, they improved engine durability and reduced the parts count to achieve lower maintenance costs. So they were going for two things here. They were going for both performance improvements and reducing maintenance costs. The first Evolution engine completed a program of it's quoted as 390 hours of ground testing. So that's on a test rig, a static test rig. It completed those in January 2010. Then it flew on the wing of the 747 test bed that you see there. Photo by Alan Radecki there, on a 60-hour certification flight test program, which was finished, I think it started May 2010 and finished only a few months later. That all took place in Victorville. The engine type certificate was then issued, I think, in August, and then it went on. So the aircraft was actually, or the engine was certified. Then it went onto the 737 for further test flight to evaluate the performance improvements of the aircraft and revise all the performance data. And the first one went into airline service in July 2011. So the whole thing was actually remarkably quick, from announcement in April 2009 to airline service in July 2011. That is really blooming quick for aviation. The photo there shows actually just the exhaust section on the wing of a test aircraft in August 2009. So they were actually trying out the exhaust configurations before the on the 7B engine before the Evolution engine was actually up and running. But more on that in the next few slides. So looking in more depth at those changes, so the PIP engine came in July 2011, and it's got the following improvements, and there are about 7 of these in total. So the first one was was in the high pressure compressor section. So the diffuser contours of the HP compressor outlet guide vane, they were optimized to improve the diffuser area ratio and reduce the pressure losses there. The OGV replaces a previous two-dimensional one, i.e. a flat, well, I say flat, obviously they're all curved to a degree because they're an aerofoil, but CFM like to refer to these as either the old one's 2D and the new one's three-dimensional. In other words, they were bowed and swept. So they look a bit more like the blades, if you like, the fan blades on the LEAP engine. You know, they're much more curvaceous, if you like. That's what they mean by 3D, bowed and swept. The second one was a change in the high pressure turbine section. These blades were also modified for aerodynamic improvements, increasing efficiency and durability. And the other thing was that the rotor count was reduced, or the blade count on this rotor was reduced from 80 to 76. And that again is weight saving, it's maintenance cost savings. I mean, again, I'm not sure if you're all aware, but as part of engine overhaul, many blades are replaced with either new or refurbished ones, and each of those has got a cost. So if you can reduce the blade count, you reduce the cost. The third change there you can see on the low pressure turbine section. This was quite a big change. So these new blades, vanes and rotors, the number of them were reduced by around about 9%. So it's quite a high blade vane and rotor count reduction. The new disc and retainers match the blade count, and the new case and shrouds match the new actual axial staggering. So it's all redesigned up there. At the back end, and this is the bit you will be able to see, there were several changes. Now, the most obvious one is this new primary nozzle, which was shortened by about 18 inches or 46 centimeters, and that's a very easy way to identify what engine you've got. If you've got the one that looks like in the picture at the bottom, you've got the Evolution engine. The picture at the top could be either the basic 7B, the tech insertion, or dual angular combustor versions. Not only was it shortened, the lines, the curves, the profiles of it were recontoured for improved nozzle coefficients and losses. There was an acoustically treated honeycomb lining built into the primary nozzle's inner wall, and the reason for that was to ensure that there was no increase in noise as a result of shortening the exhaust. Any boy racer with his first car or motorbike will tell you that if you shorten the exhaust, it makes more noise, sounds more punchy. That's great if you're trying to impress the girls with your car. But it's not good for noise pollution and noise profile. So yes, the exhaust was shortened, but this acoustic honeycomb lining offset the potential noise gain from doing this. The other change. This is a little bit more subtle, but the primary plug has been shortened by 2.5 inches. Now, I know at first glance it looks longer, and I had to reread this several times before I was convinced. But if you actually if you got an aircraft, if you got one of each nearby, you can actually see it. And the way to do it is to look at the end of the plug and just go vertically up from it and look where it meets one of the joins on the on the exhaust shroud there, and you will then be convinced that this plug is actually shorter. It's also been recontoured for improved, again, coefficients and losses. So it's been aerodynamically redesigned, in other words. Now another thing which I'll come on to in a couple of slides, but I'll just mention it here, but there's an oil drain pan and tube has been installed in there to reduce oil pooling within the plug, and as I've said, I will come on to the significance of that in a few slides. The last change was a new strut aft fairing heat shield assembly. This is the part where I said you can actually see that. In fact, I think you can see it on this photo. If you compare the upper and lower photos, you'll see that plug length and where it meets the join. So yeah, anyway, this heat shield has got new heat shield blanket, inboard plume suppressor, scoops, and a strut cover plate. And the reason for this, again, was because that exhaust nozzle was shortened. The nozzle and the plug are shortened, so you're kind of exposing the engine strut to potentially more heat source. So what these changes have done is they've reduced the thermal distress, as they call it, from that shorter nozzle configuration. So they were the changes. These are the benefits. First one is a 1% fuel saving. Now this is just from the engine alone, because the whole pit package gives you a 2% saving, and an improved EGT margin over the 7B with no noise or emissions penalty. So that's significant. Engine maintenance costs are also reduced up to 4% for the highest thrust rating, the 27K engines. The higher the thrust rating, the greater the maintenance cost improvement. So if you're operating one of the lower thrust ratings, you won't have quite 4%, but it goes up to 4% for the highest engines. Now, remember me mentioning the oil drain pan and tube in the plug to reduce oil pooling. Well, this in turn leads to a reduced likelihood of what's known as candle fires. Now, candle fires, they're a kind of tailpipe fire, but they're a quite specific one. They're caused by an accumulation of oil collecting somewhere in the engine exhaust, and you get these after shutdown. Not very often, I have to say, but this is when you'll see these candle fires. So oil collects or drips down into or runs down into a section of the exhaust that's particularly hot after flight, and ignites. Usually the vapors go first, and then that causes the rest of it to burn. Now they don't burn very hot. They don't actually trigger an engine fire indication in the flight deck, so you probably will be the last to know about it. Usually what happens is the ground staff or whatever start hopping about and saying, oh, you've got an engine fire, and trying to attract your attention. Meanwhile, we're up in the flight deck completely oblivious to this. We're seeing no indications at all. But don't worry, I mean they're not actually at all dangerous, really. Boeing and CFM have assessed these as not being a safety issue. The reason being that that all of this area is completely fire resistant, because it's used to far higher temperatures from the exhaust of the true exhaust when the engine's running, which is hundreds and hundreds of degrees centigrade higher than a little oil fire in the exhaust. Again, don't know how aware you might be of this, but not only is the strut, but the wings and are actually made fire resistant in this area, and I think it's out to a diameter of a hole in the cell's diameter from each side of the center line of the engine. So you've got twice the diameter of the engine behind it on the wings and the strut, made fire resistant for just such a reason. So a little engine oil fire isn't going to really be any biggie. And the upper photo there is a photo of, you know, the aftermath. I couldn't find any photos of a candle fire in progress, but that's what the strut will look like afterwards. Intermixing. The new Evolution engines they're fully interchangeable and intermixable with all of the previous engines. The basic 7Bs, the 7B3s, you know, your tech insertions, the SACs and the DACs, all of them. Subject to updated FMC, model engine database and EEC software. So it fully intermixable. As you can see on the photo below. Now, as regards nozzles, short and long nozzles and plugs, they can't be intermixed on any one engine. However, you can have a short nozzle plug combo on one engine and a long nozzle plug combo on the other engine on the same aircraft, as per this photo. So intermixing is pretty much every combination except within the engine is allowable. One last thing to mention is that the engine in-flight relight envelope was revised in 2012. Now, when the PIP was introduced, all the Boeing literature stated that the PIP engines were operationally transparent to the flight crew. Operationally transparent, there's a phrase. So what they meant by that is that there were no changes to the normal flight crew procedures or AFM performance relative to the previous engines. Personally, I would challenge both of those clauses, because very soon after the Evolution engine was introduced, like the very next issue of the QRH, the relight envelope was changed, and I think that's far too much of a coincidence. And flight manual performance changes. Well, we know the engine's 1% more fuel efficient, therefore there must be some changes in performance. But anywho, that's what Boeing said when you know, to herald PIP. So the in-flight starting envelope was revised in the 2012 QRH. The max relight envelope was reduced quite significantly, actually, from flight level 270 to flight level 240. So you know, you've lost 3,000 foot of potential relight space there. They also revised the procedure and put in a more formal definition of a warm versus a cold engine. It used to be just if the engine had been shut down for more than an hour, define whether it was warm or cold. The implications being whether you had to do a crossbleed or could do a windmill relight. They also brought in a 30 degrees C EGT clause as well to help decide whether the engine was warm or cold. Now, whilst I am pretty much 100% certain that this envelope, this revised envelope, was brought in for the Evolution engine, Boeing took the decision to adopt the new procedure and envelope as a common standard across the NG fleet for simplicity. In other words, to make it operationally transparent, to use their phrase, and to allow engine intermixers. You can imagine the confusion we would have in flight if we were switching between different aircraft and the relight envelopes were different, or even worse, if we had an intermix of engines. So we had an Evolution engine on one side and, say, a tech insertion or a basic 7 on the other side, and the relight envelope had to be different for each engine. So this was obviously considered undesirable, and we now have the one in-flight start envelope for all engines. There you go. That's it. That's the PIP. As always, please, if you enjoyed this video, give it a like, subscribe to my channel if you haven't done so already, and consider getting the book. It's got all of this information in it, and it's, you know, quite a good companion to the videos. Thanks very much for your attention.